Welcome friends to my YouTube channel. Yesterday I discussed about second law of thermodynamics, and there I told two statements regarding second law. One is Clausius statement and another is Kelvin-Planck statement. Okay. So what we told in Clausius statement that uh, heat cannot flow from cold body to a hot body unless and until we supply external energy from outside. Okay. And what we told in Kelvin Planck statement that it is impossible to construct a engine that can have 100% efficiency, because 100% efficiency means the entire heat taken from the source is converted to work without rejecting any heat to sink, so it is impossible. So the next thing I am going to discuss is that these two statements are equivalent. Okay. So I have to discuss on that topic, how we can conclude that these two statements are equivalent. Okay. So suppose this is a source and this is sink. Okay. That we call source and that we called sink, and we consider two engines. Okay. Working between same two temperature limits. Okay. Say this is E engine, say this is R engine. Okay. The engine E absorbs Q1 amount of heat from source and rejects Q2 amount of heat to sink, performing W equals to Q1 minus Q2 amount of work. Okay. So the performance of this engine is okay. It obeys everything, no problem. Okay. So E engine is perfect. E engine is perfect. That is, it absorbs Q1 heat from source and rejects Q2 heat to sink, performing Q1 minus Q2 amount of work. Okay. Amount of work. So this engine is perfect. Okay, no problem. Now suppose the R engine absorbs Q2 dash amount of heat from sink and convert the entire amount of heat to source. That is, suppose this engine okay, absorbs Q2 amount of heat and gives the entire heat to source requiring no work. Okay, so mainly we assume that this violates Clausius statement. Okay, this violates Clausius statement. Okay, যে suppose R engine absorbs Q2 heat from sink and rejects Q2 heat to source without requiring any work, without requiring no work. So it is impossible. That means we don't supply energy from outside, then the entire heat goes from sink to source. So this is not possible. So there is a violation of Clausius statement. That means this engine violates Clausius statement. Okay, we have to assume that Clausius statement. Okay, so that we assume that our engine absorbs a particular amount of heat and rejects that same amount of heat requiring no work. So there is a violation of Clausius statement. Okay, that means minus C. Minus sign means violation and C means Clausius statement. So there is a violation of Clausius statement. Remember it and we assume that. Okay, so here we consider the two separate functions of both the engines. The engine E is okay and the engine R violates Clausius statement. Now what would happen if these two engines are coupled together? Let's check the function of the coupled engine. Okay, let us check the function of the coupled engine, and the performance of the coupled engine will tells us everything. Okay, so let's check that what is the performance of the coupled engine. Okay, so if we draw a coupled engine by using this diagram, then what would be the coupled engine? What is the function of the coupled engine? Just simply this simply this, and clearly see, if they constitute a self-acting device, then self-acting device absorbs how much amount of heat from source? The net amount of heat, that is Q1 minus Q2 amount of heat. ঠিক আছে, যে E and R if coupled, then they constitute a self-acting machine. Constitute a self-acting machine that absorbs Q1 minus Q2 heat from source. Okay, so coupled engine absorbs Q1 minus Q2 amount of heat from source. Okay, and you see, in this case individually the R engine requires no work and the E engine performs this work. So what will be the total work done by the coupled engine? The total work done by the coupled engine is Q1 minus Q2, and this is also Q2, this is also Q2, and the net amount of heat rejected to sink is 0. So heat rejected to sink is 0. Rejected to sink is 0. So the function of the coupled engine is such that it absorbs heat Q1 minus Q2 from source and convert the entire heat to work without rejecting any heat to sink. So this is not possible. So there is a violation of Kelvin-Planck statement. Okay, so the coupled engine violates Kelvin-Planck statement. Okay, we can clearly see that the coupled engine violates Kelvin-Planck statement. Okay, that we clearly see that the coupled engine violates Kelvin-Planck statement. Okay, the coupled engine violates Kelvin-Planck statement. Okay, so coupled engine violates Kelvin-Planck statement. So we arrive this point by considering that our engine violates Clausius statement. That means from starting with the violation of Clausius statement, we arrive the violation of Kelvin-Planck statement. That means minus say this is equal to minus K. We start here, we made the assumption that Clausius statement is false. then we arrive at the result that Kelvin-Planck statement is always false. So this proves that these are equivalent laws, because if we get opposite result, then we can easily conclude that these two statements are not agree with each other, but after by taking the violation of one statement we arrived at the violation of the another. So Clausius and Kelvin-Planck statement are equivalent. Okay, so this is the logic behind it. You have to understand this concept, that how these two laws agrees. Okay, so with this I completed the second law of thermodynamics and heat engine. Okay, now we will do few problems and numericals of second law and of first law in our next class, that we will start from our next class. But today I shall give a brief introduction of my third chapter, that is entropy. I have to give a brief introduction of entropy. Okay, I have to give a brief introduction of entropy chapter. Okay, now at first, what is entropy? We all know that entropy, this is the chapter 3, entropy chapter 3. So what is entropy? The basic is that we all know that in adiabatic process there is no exchange of heat between the system and surroundings. Okay, so we know it. So there is no exchange of heat between the system and surroundings, that means dq is 0. Now again we know from second law that second law can be stated in terms of entropy, that we will discuss later. So from second law again we know that if a system absorbs dq amount of heat at temperature T, then we all know the entropy ds equals to dq by T. Okay, the system absorbs dq amount of heat at temperature T, then the increase in entropy is this. So uh, dq is 0 for adiabatic process. We all know that there is no exchange of heat between system and surroundings. Okay, so if we put dq here 0, then ds is 0 and that s is constant. So you can give a definition of entropy from the second law of thermodynamics. So uh, this gives the definition of entropy from second law of thermodynamics. So what we can write the definition of entropy? Uh, the quantity which remains conserved during adiabatic process when there is no exchange of heat between the system and surroundings is called entropy. This is the definition of entropy. Okay, this is the definition of entropy. The quantity that remains constant during adiabatic process when there is no exchange of heat between system and surroundings is called entropy. Okay, now the second thing is that what are the basic properties of entropies. Okay, and we will discuss it. So at first let us understand what are the basic features of entropy. Okay, What are the basic properties of entropy? Okay, so let's check what are the basic properties of entropy. Dear guys, kindly ignore the sound which was coming from outside, which is coming from outside. Ignore it. So, first property is that entropy is a measure of disorder of a system. What is disorder? Now, suppose there is a tray and there are five or there are few red balls, and suppose there is another tray in which there are few yellow balls. Okay, so if you mix them together, then the randomness of the system increases. If you mix them together and keep it on another tray, then the entropy, that is the disorder of the system, increases. Okay, this is called disorder. So mixing, if you mix them in a single tray, then the disorder of the system increases. So it is nothing but disorder of a system. Entropy represents the disorder of a system. Okay, and we took an example. If there are few red balls in a tray and there are some yellow balls in another tray, and if you mix them, then the randomness of the system will increase. So it is a measure of disorder of a system or randomness. Okay, next one thing, that it is a single valued state function like internal energy. It is a single valued state function. What is that? Single value means, suppose this is a system, it is the initial state I and this is the final state F. So in initial state there will be only one value, that is Si, and in final state there is only one value, that is SF. That is, at a particular state there is only one value. That is called, it is a single valued function. And why state function? Because it only depends upon the values of initial and final state, no matter through which the system moves from initial to final state. Okay, the system can go from this path, from this path, or this path, or this path, no matter in which path the system moves from initial state to final state. That is, it is path independent. Among these paths through which the system moves from, choose any path, then it does not depend upon the path, it only depends upon the values of initial and final states. So that is why it is not a path function but a state function, only depends upon the initial and final state. And third one is that absolute value of entropy cannot be measured. Absolute value of entropy cannot be measured. Only we can measure the change in entropy if we moves from one state to another. Only we can measure the change in entropy, that is ds, that can be measured. So suppose there is a problem in which it is given that a system has an entropy, suppose say 50 unit SI. So that means ds is given, not SI, not SF. So if they are in a problem, it is given that entropy of a system is 50 SI unit, it means the change in entropy, that is ds, is given here. Okay, not the absolute values, they cannot be measured. So okay, now another important property is that ds is a perfect differential. That means line integral ds is 0. Okay, ds is a perfect differential means the line integral of ds around a closed path is always 0. And whenever any differential term can be expressed in this condition, that means it is a perfect differential. Not only ds, but du, dp, dv, dt, these are also perfect differentials. Okay, perfect differentials. Okay, this is the condition of perfect differential, that is line integral ds is 0. And another condition is that suppose entropy is a function of xy. So the condition of perfect differential is what? The condition of perfect differential is del 2s del x del y. This must be equal to del 2s del y del x. Okay, so this is also another property of entropy. Okay, so in our today's class we have discussed the basic properties of entropy. Okay, and we also discuss about the equality or clause equivalency of Clausius and Kelvin Planck statement. Now in our next class we will discuss about few other basic properties of entropy and we will explain it. Okay, so dear guys, if you don't subscribe my channel, then kindly subscribe it and share it to your friends to get latest videos. Thank you.